Hi, I'm Joe from Class 3E. Today, we will be presenting the design of the AI patient monitoring system for the new Kaidak New Acute Hospital, as well as the network, data, and security behind it. You might be wondering what an AI patient monitoring system actually is. An AI patient monitoring system is a combination of medical sensors, hospital networks, databases, and AI software that continuously collects, analyzes, and interprets patient data in real time. The main goals of the system are early detection of problems, reduced workload for doctors and nurses, as well as data-driving decisions. To elaborate, the system can spot warning signs such as irregular heart rate, oxygen drops, muscle fatigue before they become emergencies. The system can also filter thousands of data points into a few clear, prioritized alerts. Finally, the data-driving system can give doctors visual trends, predictions, and AI summarize to support diagnosis. AI technology can be implemented to turn the basic monitoring systems into hospitals into a smart assistant that watches trends, learns each patient's normal patterns, and warns doctors. Let's take Muscle Minders as an example. Muscle Minder is a rehab product focused on improving the flexibility of the arms of stroke patients through base-shaped curls. A color sensor detects how many times you did be kept curls and displays on the application of Muscle Minder with a chart. However, we can implement AI to upgrade it into a smart AI rehab coach. Firstly, more IoT sensors can be added to detect number of curls, speed, range of motion, rest time, and weight. The device sends every section to a secure database. A camera or motion sensor tracks the arm path. AI analyzes arm movements and gives real-time feedback to the patient. Daily targets can also be recommended through this system. AI can learn by comparing each new section with the patient's history and many other users, and thus continuously learns and sends smarter preventive alerts, improving its system. The same IoT and AI ideas can be applied to other systems in the hospital to greatly help patients and doctors. For patients, the AI system has faster response in critical situations, with better rehab and recovery tracking of muscle strength, mobility or sleep. For doctors and nurses, a dashboard which summarizes progress, shows trends, and predicts problems, can show who needs attention first based on AI-calculated risk scores. Automatic logs and graphs are also provided, so there is no need to manually chart every reading. AI-generated summaries may also be included for further convenience. In a hospital AI monitoring system, both wired and wireless connections are needed, each serving different purpose. Wired networks, such as internet and fiber optic cables, are used for the core infrastructure and fixed equipment. They are extremely reliable because they are not affected by walls or interferences, and are generally more secure since physical access is required to connect. These wire links are ideal for connections between wards and the data center, as well as stationary devices such as nurse stations, servers, MRI machines, and central monitoring systems. For example, the cables can handle the massive data load from hundreds of patients' sensors and the high-resolution MRI scans simultaneously without any slowdown.
Hi, I'm Alfred. On the other hand, wireless technologies like Wi-Fi or Bluetooth provided through access points are essential for mobility. They allow patients wearables, mobile cards, and doctors' tablets to move freely around the hospital. Wi-Fi 6 is suitable for bedside monitors that may be moved between rooms and for handheld devices used by doctors and nurses. Bluetooth is useful in a technology-powered hospital, and is used for low-power wearable sensors on patients, which send data to a nearby bedside gateway. The whole network of the hospital is multiple LANs, with each building of the hospital being a LAN for each patient. The AI monitoring system will be connected to the switches of each ward using a star topology, with the switch in the center. The switches of each ward also connected to an access point for wireless access. A three-tier architecture can be adopted to handle the scalability and manageability problems of a massive network. A central core switch connects to distribution layer switches for each ward or department, which then connect to XX switches for individual rooms. Cabling and switch ports costs are much lower. The layout is clear and structured, which makes it easier to design and maintain. If a problem occurs, it typically affects only one part of the network, rather than spreading throughout. Adding new departments is simple and cost-effective by connecting a new switch to the core. Now I'll pass the time to Joe.
The single biggest security risk in a hospital network that transmits highly sensitive patient data is not just hackers on the internet, but unauthorized access to patient records through compromised endpoints and credentials. In practice, this usually happens when an attacker gains control of a weakly secured device, for example, an unpatched IoT monitor, an old PC, or a staff laptop, or steals login details through punishment, weak passwords, or shared accounts. Once inside the internal network, the attacker can often more literally from device to device until they reach systems that store or process medical records, AI outputs, or real-time monitoring data. This is especially dangerous in healthcare because temperate data can affect clinical decisions, and leaked data can cause several privacy, legal, and financial damage. The combination of many different devices, IoT sensors, bedside monitors, tablets, servers, and PC staff who must log in quickly creates a broad attack surface where one weak link can expose the entire system. Because of this, strong encryption for data in transit is absolutely mandatory. The network must use end-to-end encryption based on TLS 1.3 with AES 256 as the core method for protecting patient information, and it moves between sensors, gateways, servers, and user devices. TLS stands for Transport Layer Security. It's the same family of protocols used for secure HTTPS connections on the web. But in a hospital environment, it has to be applied consistently to all application traffic. Not only web browsers, every data stream carrying patient information, whether it's from an ICU monitor to the central server, from an AI inference engine to a doctor's tablet, or from a rehab device to a cloud database, should be wrapped into a TLS 1.3 section. Inside the TLS section, the symmetric encryption algorithm should be AES 256. AES is a modern, widely trusted block cipher, approved by standards body around the world and considered secure against current practical attacks. A 256-bit key length provides a very high security margin suitable for long-term protection of medical data. To establish the S keys securely and avoid reuse, the TLS 1.3 handshake should use ECDHE, which stands for Ephemeral Elliptic Curve-Driven Hellman Key Exchange. This gives perfect forward security, meaning that even if a server's private key is stolen in the future, previously captured encrypted traffic cannot be decrypted. This is critical in healthcare, where patient data may need to remain confidential for many years. For connections that traverse external networks, such as between a hospital and a remote clinic, or between the hospital and a cloud service providing AI analysis, the same principle applies. At a lower layer, the organization should deploy IPsec or SSL VPN terminals that also use AES 256. Within strong, modern cybersuits, these VPNs create an encrypted pipe over the public internet, ensuring that anyone intercepting the traffic cannot read or modify the contents. In addition, mutual authentication with digital certificates and multi-factor authentication for staff access helps ensure that data is only decrypted by trusted system and users. In summary, the main security danger is that an attacker gets into the internal network and reaches unencrypted or poorly protected data by abusing vulnerable devices or stolen logins. The required countermeasure at the transport level is end-to-end encryption using TLS 1.3 with AES 256 and strong key exchange. For all patient-related communications, backed up with AES-based IPsec or SSL VPNs. When traffic crosses untrusted networks, this combination makes intercept traffic effectively useless to an attacker and forms a critical foundation for protecting sensitive patient data in the modern hospital environment. This is the end of our presentation. Thank you for listening.